Hello, in this video I wanted to show you guys how to use shaders to graph 2D functions. Sometimes when I'm making a shader and I'm using a formula to affect a gradient of some kind, it helps me to actually plot the function on a graph to see the curves. So here I am in Desmos with an example. You might be familiar with this function format used for linear equations. This is called slope-intercept form. Y equals mx plus b, where the variable m controls the slope and b controls the y-intercept, which is the y-coordinate of the line, where x equals 0. Adjusting this lets you translate the line across the graph. This form of linear equation is useful when we simply want to affect the slope of the line, or how quickly values change across each axis. Then there is what we call standard form, usually written like this: ax plus by equals c. Because the expression ax plus by is equal to our variable c, we can say this equation is in terms of c. It can be helpful sometimes to write this equation in terms of one of our axes, so let's use y. If we do some algebra, it should be written like this. This way, in code, for any x-coordinate, we can find our y value. So in this form, we can make a horizontal line by setting a to 0. If we set b to 0 in this form, we get undefined because you can't divide by 0, so we don't get a line. So this is another reason why standard form is useful, because if we set b to 0, we get a vertical line as well as a horizontal line if a is 0, because we're not dividing anything by 0. And then there's another interesting way we can write this equation we'll call general form. This is when we take the same equation and set one side of the equal sign to 0. This form is useful because it allows you to pass any x and y coordinate into this equation, and it will result in 0 like this if the coordinate lies directly on the line, or a positive value if the coordinate is on one side of the line, and negative if it's on the other side. And the magnitude of this positive or negative number is how far from the line the coordinate is. We can even take the slope-intercept form of the line and refactor it so 0 is on one side of the equal sign, like this. This is exactly what we need in order to easily visualize this function in a shader, because then we can just pass the UV coordinates into this equation and get a gradient to display the line function. So now let's hop into a shader to do this. So in a new 2D scene in Godot, I'm going to make a margin container and set the size to 1024 by 1024 pixels. And I'll add a color rect so we can see our shader. And now I'm just adding a shader to the color rect. Let's make some uniforms for our line equation. I'll just start with slope-intercept form with m and b. Now down to the fragment function, I'll make a new float called line. And now we basically write out our equation in this general form. For x, we use the x component of the UV coordinates, and y for y. And then we can just set the fragment color to the value of line. And now you can start to see our gradient. Since our UV values are between 0 and 1, the gradient we see is very gradual across the entire UV space. We can scale the gradient by taking our line and multiplying it by a new float called scale. I'll make it uniform so I can adjust it in the editor, and I'll just set it to 100 for now. Now you can see how the scale value tightens our gradient significantly, and we can really see the line. You'll notice one side of the line is black and one side is white. This is because the line values for coordinates on the back side are negative and the other side are positive, and the coordinates on the line itself result in a value of 0, which is still black. This might be all you need for your applications, but if you want to show a black line against a white background, you can just take the absolute value of this line function before we apply the scaling. And then if you want to control the thickness of the line, let's add another variable for thickness and just subtract the thickness from your line before applying the scale. Cool. Now let's play with our line function. One thing we can do is visualize the output of the smooth step function this way. All we have to do is apply the smooth step function to the x value in our equation. And we will set the edges of the smooth step function to 0 and 1. And here you can see that the slope m controls how quickly values ascend towards 1, and b controls the x-axis shift of the smooth step line. Alright, so let's try a quadratic equation. There's two ways we can write this function: in standard form using a, b, and c as line parameters, or we can use a form similar to slope-intercept form, which is called vertex form for quadratic equations. It is called this because the parabola of the line reaches its minimum or maximum at a certain vertex whose coordinates are equivalent to h and k. I'm going to use vertex form. And now I can set both h and k to be 0.5 so the parabola appears in the center of the screen. Nice! So that's a quick way to visualize 2D functions in a shader. Sometimes I do this when I'm applying a linear or curve function to a value and I'm not getting the results I want, so I just make a variable for the line and pass it into the color channels of the shader to see how the line function works. I hope this helps some of you with your shaders. Thanks for watching.